Hello friends, so I had a network problem. So I would like to start uh, where I had ended my last lecture. So okay, so I would like to recall that. So my topic was I selected the topic that irreducibility test of polynomials, which is very much important in many exams. Uh, many exams uh, in CSIR NET, NBHM TIFR, so for PhD entrance tests in mathematics. So this topic is very much important and you need to know the basic ideas and facts. So what is what? So that is very important. Uh, and in this connection, I have already discussed the preliminary parts in my previous lecture. Uh, so I would like to recall the statement of the theorem that I have already discussed in my previous lecture, which was that let fx be a polynomial x to the power n plus an minus 1 x to the power n minus 1 plus n minus 2 x to the power n minus 2 plus dot n a1 x plus a naught, where the has been uh, coefficients have been taken from the ring of integers. That is, this is a polynomial over z, having a condition that the constant term a naught is not equal to 0. Uh, okay, fine. So then it says that if fx has a 0 in Q, uh, that is, if fx has a 0 in the field of rationals, then it has a 0, say it is k, and the 0 lies in the ring of integers set. So it has a 0 in the ring of integers z. Having satisfied the condition that this k should divide a naught. So this is very crucial part of this theorem, and using this result you can deduce that a given polynomial over z is irreducible or not over uh, q. And okay, so uh, so k divides a naught. So this part is crucial because you have a choice of k and it must be a divisor of a naught. So with this choice, so these k's are restricted to the set of divisors of a naught. And since it is a finite set, so you can easily uh, obtain the coveted goal that you want to show whether the polynomial is irreducible over Q or not. And in using this theorem, I have already discussed 2-3 examples that how to uh, tackle the problems of irreducibility using this one. So, yeah. So now today I would like to put light on another famous test of irreducibility over the field of rationals, although this test can be extended to uh, any integral domain and over its field of quotients. So yeah. So Eisenstein, this test is named after Eisenstein, and this test says that. So I would like to write down the statement of the test, Eisenstein test for irreducibility. Yeah, irreducibility. So this is very famous sort of result in the polynomial ring, and very much important to deduce irreducibility using this theorem. Okay. So what is the statement? The statement says that first of all you need to choose a prime. Yeah. So let us consider a prime number p, and so this part is important. That choice of p is very much important, and I will just tell you the fact that how to choose this prime. So this is very crucial for this test. And now let us uh, consider a polynomial fx, which is an x to the power n plus an minus 1 x to the power n minus 1 plus a1x plus a naught, which is a polynomial over the ring of integers. Yeah. So you may take any polynomial over the ring of integers. Okay. Now this prime will work for this polynomial in this way. That is, if the n, the coefficient n, if it is not congruent to 0, that is, this is a polynomial with these conditions in connection with the prime number p that I have written. So what are those conditions? The first one is n is not congruent to 0 modulo p. That means this prime will not divide this leading coefficient. But in case of other coefficients, yes, it will divide. That is, all other coefficients are congruent to 0 modulo p. That is, p will divide all other coefficients except the leading one. That is n. So this is true for k less than n. Yeah. Okay. And the last condition is that the constant term a naught, although p will divide a naught, but P square will not divide A naught. So A naught is not congruent to 0 modulo P square. So having satisfied these conditions, the polynomial effects that we have chosen will be irreducible over Q. So this is the conclusion of this test, that if this polynomial will satisfy these conditions with respect to a prime P, then the polynomial over Zx, that is over Z, is irreducible over its field of quotients, which is Q. Q is the field of quotient of the integral domain of integers. This is a standard result in ring theory, that any integral domain can be embedded into a field, and which will be the field of quotients, and it is a general result. And using this fact, you can construct the rationals with the help of integers by defining an equivalence relation uh, between z and its non-zero uh, integers. Yeah. Okay. So let me come back to this fact. So then fx is irreducible over q. So this result tells us that if fx is a polynomial over the ring of integers, and if it satisfies the following conditions, that is, first one is p will not divide the leading coefficient n, but p will divide all other coefficients, although p square will not divide the constant term. Yeah. So with respect to this prime, if this polynomial will satisfy these conditions, then you can conclude that this polynomial must be irreducible over Q, over rational. So I am not going to prove this theorem, because I would like to just put light on the fact that how to deal with the problems using this irreducibility test. So this is a very important test in ring theory. Okay. So uh, okay. So let us first just write down a problem that, okay. So in my previous lecture, I have uh, proved that the polynomial uh, x square minus 2, this, okay, this polynomial x square minus 2 over z. So I have already shown that this polynomial is irreducible over Q using the theorem that I have written down at the beginning of my today's lecture. Okay. Now the same problem can be tackled with the help of Eisenstein criteria. But how? Now the first crucial part of this test is to choose the prime. So you need to choose a suitable prime so that it will work for this polynomial. Okay. Okay. So now if you look at the coefficients, so what are those? So this is x square plus 0x minus 2. Now if you look at the coefficients, you will find that the prime should divide all the coefficients except the leading one. So here the leading coefficient is 1. Yeah. and all other coefficients are, one is 0 and another one is -2. So if you want to apply the division process, then you will find that these two coefficients can be uh, divided by uh, the prime number 2, because 2 can divide 0 and -2 both, and 2 is a prime. So this is your first choice of prime, that okay, p may be taken as 2. The prime is 2. And also if you choose this prime, then it will work for the leading one also, that is 2 will not divide 1. Yes. So these conditions, the first two has been satisfied by this prime and the coefficients of the polynomial. Now let us have a look at the last condition, that is p square, whether p square will divide the constant term or not. Now what is p square? P square is, here p is 2, so p square is 4. So 4 will not divide -2, as -2 is less than, strictly less than 4. So 4 will not divide -2. Okay. So our choice of prime uh, satisfies the conditions of the test, Eisenstein's test for irreducibility. So hence you can conclude that using this test, that this polynomial x square minus 2 is irreducible over Q. Yeah. So what I would like to uh, stress on the fact that you need to choose a suitable prime, keeping in mind the coefficients of the polynomial. So look at the coefficients of the polynomial first, then decide what will work for this polynomial, which prime will work for this polynomial. So this is a crucial one. So in many cases you will not be able to find out the prime very easily. So this is uh, a drawback of this uh, test. Okay. Okay. Similarly, if I can write down another problem, let us have a look at the problem. That is, if we consider the polynomial 25 x to the power 5 minus 9 x to the power 4 plus 3x square minus 12. Then over the field of rationals. Okay. Then what to do? We need to apply the test, Eisenstein test for reducibility. So let us have a look at the coefficients. So it is 25 x to the power 5 minus 9 x to the power 4 plus 3x square plus 0x minus 12. So the leading coefficient is, here a5 is 25, a4 is minus 9, a3 is 3, a2 okay, we need to put 10 here, 0x cubed. Yeah. So a3 is 0, a2 is 3, and a1 is 0, and A naught is minus 12. So we would choose the prime as so as to divide all these coefficients from A4 to A naught. So what will be the suitable prime that we must choose? As we are looking at the coefficients, we find that you can choose 3. You can choose 3 as a prime because 3 will divide all these A4, A3, A2, A1, A0. So this condition has been satisfied by this prime, by this prime 3. Yeah. Now we need to check that whether it will divide the leading coefficient or not. But in that case, 3 will not divide 25. So second one is also satisfied by this prime. And the third one is 3 square, that is 9. Now 9 will not divide the constant term minus 12. So by the use of this prime, you can easily check that this polynomial is not so reducible over Q. That is, so by Eisenstein criteria, you may write down that, you may conclude that this polynomial is irreducible. So this polynomial is irreducible. Okay, irreducible over Q. Yeah. Okay. So this is a beautiful problem. Okay. Now another important problem that I must encounter in this lecture, that is the polynomial over Q, and which is like that. The polynomial is for a prime P which is x to the power P minus 1 by x minus 1 over Q. Yeah, over Q. So that is, it is the polynomial which looks like x to the power P minus 1, x to the power P minus 2, x plus 1 over Q. Now here, if you are to show that this polynomial is irreducible over Q, then, and if you are to invite the irreducibility test due to Eisenstein, then you will see that the coefficients all are 1. So how do you choose a prime? Because all the coefficients are 1 here. From this one to the constant term, all these are 1. So how could you choose the prime? So you may stuck at this problem that is not possible to choose the prime P out of the coefficients of the given polynomial. And for this problem, you need to go for a trick. What is the trick? The trick is that just give a translation, that is x plus 1. And if you do this one, then you will find that this will be like that. Yeah. Fine. So now this expression can be simplified as, so you can check on your own that this can be written as x to the power p minus 1 plus uh, pc1 x to the power p minus 2, so on p. p. So now you see that for this polynomial you have coefficients where p involves. Where p involves. Yeah. So with this expression you can invite Eisenstein criteria with respect to a suitable prime. But in that case, your constant term is p. So the prime must be the p itself. Okay? And using this prime p, you will find that p will divide all those coefficients of the terms x to the power p minus 2, x to the power p minus 3 and up to the constant term. So p will divide all those coefficients from a p minus 2, a p minus 3 and so on. And the last one is a naught, which is p. Yeah. And p will not divide 1 because the leading coefficient is 1 here. So p will not divide 1. And the last condition is p square. Now what is now p square? So p square will not divide p, as p square is greater than, strictly greater than p. So how it will divide p? So it will not divide p. So p square will not divide the constant term. And having satisfied these conditions, you can conclude that this polynomial is irreducible over Q. So by Eisenstein criteria, you can conclude that this polynomial phi px plus 1 is irreducible over Q. Yeah. But your problem was to tackle with the polynomial phi px. So you need to go further using this fact that phi p x plus 1 is irreducible over Q using Eisenstein criteria. Okay. Now let us suppose that the polynomial that you have chosen phi px, suppose it is reducible, that it can be factored into two polynomials hx and rx, where hx and rx are both are non-trivial polynomials, non-zero polynomials, non-zero non-constant polynomials, okay, in zx. So phi px can be factored into two polynomials hx and rx. If this holds, then again applying the translation to phi px, you will have, so phi px plus 1 will be hx plus 1 rx plus 1. Okay. So then this will give a non-trivial factorization of phi px plus 1 in zx. Okay. But this will contradict our proof of the irreducibility of phi px plus 1 over q. So this contradiction gives you the answer to this problem, that phi px is actually irreducible over q. So phi px must be irreducible over q. Okay. So hope you will enjoy this session, and uh, you can use this criteria to check the irreducibility for many polynomials over q, and this criteria is very much useful in many cases. So this is very important criteria, and you need to have a deeper view of this criteria to check the irreducibility of polynomials using this. And you should know that this criteria can be extended to a general integral domain and over its field of quotients. So, okay, it's a general criteria, not that it holds for z over z and q, not that. It holds for any integral domain and over its field of quotients. Okay, so I would like to stop here, and in the next irreducibility test, I would like to put light on another beautiful criteria that is generally not in the general courses that you are going through, uh, but this test is very much useful in certain cases, and it's very easy, but it has a beautiful look on its own. So I would like to stop here. So if you like my video, please like, share and subscribe my channel, and if you feel that it deserves to share, please share with your friends, those who are interested in mathematics, those who wants to learn mathematics. Don't go for any short trick to learn mathematics. There is no shortcut to learn mathematics. Thank you for today.